Hello everyone, today is Thursday and we are starting the third class within the course Survey of Optimization offered by the Department of Postgraduate Studies of Viktor Glushkov Institute of Cybernetics of the National Academy of Sciences of Ukraine. I recall that the course developer is Butenko Sergey. The course advisor is Piotr Ivanovich, and I am the course instructor, Valery Ivan. Today we will continue our topic regarding mathematical programming and concentrate on how IT technologies can be used in order to simplify time and energy-consuming computations, which might involve a great number of iterations before the final solution is generated. Specifically, we will speak about optimization solvers, which embed a powerful algorithm and that can solve mathematical programming models, constraint programming, and constraint-based scheduling model. The agenda of today's lecture is covers the NEOS server, its overview, structure, general characteristics, etc. Specifically, we will introduce Gurobi optimizer, minus optimizer, Baron optimizer, and C-Plex optimizer. So there are many more solvers actually offered in the market. And among the mathematical programming languages, we will introduce GAMS, General Algebraic Modular System, and AMPL, a mathematical programming language. And of course, we will solve some optimization problem examples using AMPL with different optimizers. So let's go ahead. Problems of mathematical programming and numerical methods of solving them are constantly being improved and changed. Effective numerical methods which have been developed can be used for a specific application or for solving a wide range of optimization problems through network-enabled optimization system. Here it is, which is a server that allows the user to solve optimization problems online. So the NEOS server is one of the platforms that can be used for finding solutions for a variety of optimization models. As it was said before, the NEOS server is an internet-based client-server application that provides free access, free means free of charge access, to a library of optimization solvers. Its library of solvers include more than 60 commercial, free, and open source solvers, which can be applied to mathematical optimization problems of more than 12 different types, including linear programming, integer programming, and non-linear optimization. The NEOS server reference is at the top of the slide. It's next to the heading, as you see. And there is some historical facts, I would say. First, the server was developed in 1996 and introduced to the market, I would say, by the Optimization Technology Center of Argonne National Laboratory and Northwestern University, both located in Illinois, the state of Illinois, of the United States of America. The objective was to develop a method to share optimization software resources over the internet. It is managed by the Wisconsin Institute for Discovery and the Institute of Wisconsin Medicine. And therefore, of course, most of the solvers are hosted by the University of Wisconsin in Madison, though it also supports several remote solvers, which are hosted by its partner organizations, specifically Arizona State University, the University of Klagenfurt in Austria, and the University of Minho in Portugal. The NEOS server connects the user and the necessary software and the necessary software for solving optimization problems. It accepts the described optimization problem and returns the solution in interactive mode or email. Optimization applications allow the user to focus on the description of the model optimization problem. Users do not need to download and install software for optimization on their computers, which significantly saves the space occupied on their drivers. The tasks are solved on a cluster of high-performance computers controlled by the HT Condor software, a specialized system for managing side load for work with intensive high-performance calculation. Like other full-featured batch systems, HT Condor provides a task queue management mechanism and prioritizing the implementation, monitoring, also monitoring and resource management, and it can be used to manage workload on a dedicated cluster of computers or to farm out work to selected idle desktop computers. The current NEOS administrators come from the University of Wisconsin-Madison, and they are Michael Ferris, Ben Hubner, Jeff Linderoth, Elizabeth Wong. Interestingly, is that the development of the NEOS server was partially supported by various grants from the Office of Advanced Scientific Computing of the Department of Energy and the National Science Foundation. Now, as you see from this graph, the platform supports and can solve a wide variety of optimization problem types. As it has been mentioned before, its library of solvers includes more than 60 commercial and free and open source solvers, which can be applied to mathematical optimization problems of more than 12 types or even more, of course, including linear optimization, linear programming, integer programming, non-linear actual optimization, and so on and so forth. So as we discussed last time, different types of optimization models, so depending on the types of variables involved and the objective function actual type, so it can actually handle the problems of continuous optimization, discrete optimization, unconstrained, constrained optimization under uncertainty, which refer to stochastic programming, and so on and so forth. So here you see some of the available solvers. We will refer to some of them today and discuss them in more detail. And the website, the submission website, which helps you to submit the assignment and to get a solution for the model without downloading any software, looks like this. And at the end of this lecture, actually, we will solve some problems using this site form. And as we spoke about, and I forgot to say that the main mechanism for the main mechanism for solving optimization problems using the NEOS server is that the user writes a specification for a particular problem and submits it through one of the established interfaces. Note here, for example, it's submitted. Upon receipt, the server gives the task its number, password, and puts it in a queue for conducting calculations on one of the remote computers and servers. As soon as the task is received, it gets decoded, the driver processes it, including performing the required computation. Task processing involves computation of necessary derivatives and linking libraries of algorithm and objects. Then the optimization code is executed on the server, for which a maximum of 8 hours is allocated. After completing the calculations, it is removed. The computer reports the results to the server, which transmits them to the user interface, and one of them, for example, to email. One of the, as we have mentioned, actually, some of the solvers, one of the optimizers and solvers which are widely used and which are quite popular now is Groby optimizer. It is a special kind of software called a solver, developed by Robert Bixby. Later we will refer to this name again. Zonghao Gu and Rotherberg founded it, Groby, in 2008. It supports 3 modeling languages, among which are AMPL, GMS, and MPL. Supports interface of the programming, such programming languages as C, C++, Java, Python, MATLAB, and others. It is very good for large linear and quadratic programming models, mixed integer programming, non-linear programming models. And later on, actually, when we will decide, you will see how often the solver is used and how many problems it can solve. It uses a unique combination of genetic algorithm and classical non-linear optimization method. Now, next, optimizer, which again will be used in which is very popular, of course, and in some systems even goes on default, is Minus, a modular in core nonlinear optimization system. The peculiarity of this optimizer is that it is a Fortran-based software package for solving linear and non-linear mathematical optimization problems. It was developed by Bruce Murta and Michael Saunders at Stanford University, USA, of course. It remains one of the top used solvers on the NEOS server and in their language GMS. It supports such type of problems as linear, quadratic, and smooth nonlinear objectives and constraints in continuous variables. And the specific feature of this optimizer is that it handles linear constraints separately from nonlinear ones for greater efficiency. Now, another optimizer which we will use in this course will be Baron optimizer, and we will try it again, which is an acronym which stands for Branch and Reduce Optimization Navigator, from the optimization firm which developed it, USA, located in the USA. The product is the result of nearly 30 years of academic research and recognized by the Informs Computing Society Prize and the Bill Orchard Hayes Prize for excellence in computational mathematical programming. It supports such types of problems as linear programming, non-linear programming, mixed integer programming, mixed integer nonlinear programming, and maybe some more. Supports such modeling languages AMPL, GAMS, AI, and MS. And one more popular optimizer is Cplex. Cplex was the first commercial linear optimizer on the market to be written in the C programming language. The name Cplex comes from the simplex as a method and C as the programming language. So being combined together, it resulted in the name of Cplex. This is a high-performance optimization solver for linear, mixed integer, and quadratic programming. Originally developed by Robert Bixby, actually we mentioned it before, in 1987. It supports such types of problems as linear programming, non-linear programming, integer programming, mixed integer programming, and quadratic programming problems. interestingly, that it supports interfaces with such programming languages as C, C++, Java, Python, MATLAB, Excel, and supports such modeling languages as AMPL, GAMS, AIMMS, and others. So, as we have just mentioned, so about modeling languages, so we will introduce two of them. The first one is GAMS, mostly because it was one of the first general algebraic modeling system, started as a research project at the World Bank in 1976, although in 1987 it already became a commercial product to be marketed in worldwide. That is the first algebraic modeling language similar to commonly used fourth generation programming languages. It has a high level modeling system for mathematical optimization and designed for modeling and solving linear, nonlinear, and mixed integer optimization problems. Allow the users to implement a sort of hybrid algorithm combining different solvers, and is one of the most popular input formats for that NEOS server. Now, later when we visit the site, you will see how often this language is used. And another mathematical programming language, which we will use within the scope of this course, we will concentrate on it. So that's why we are introducing is AMPL, an acronym for mathematical programming language. In the professional slang, especially among native speakers, this acronym is often pronounced as AMPL. So some historical facts. It was developed by Robert Fourier, David Gay, and Brian Kernighan at Bell Laboratories, and first designed and implemented in 1985. This language supports dozens of solvers, both open source and commercial software. Its syntax similar to the mathematical notation of optimization problems, and it is available for many popular operating systems, including Linux, Macintosh, and Windows, actually, which will be mostly used by us. Also, it supports a wide range of problem types, which involves linear programming, quadratic programming, nonlinear programming, mixed integer programming, global optimization, and so on and so forth. For references, it is recommended to visit https://ampl.com site, which provides a free download student versions of AMPL and representative solvers that run on Windows, Unix, Linux, and Macintosh. Also, it provides a book which carefully instructs for this language, which is still available on this site under the tab resources. And also on the same site under the tab Try AMPL, you can watch a free demo about this. No, and this is actually the logotype here you see of this language. Now, how it works. Now, let's talk about AMPL's role in the modeling process. So when you learn optimization models in class or in the textbook, we tend to write them in the form of algebraic functions, equalities and inequalities, like we did before in the previous lecture. Remember that we put the objective function, maximize, minimize, then using algebraic symbols, then using algebraic symbols, we wrote down inequalities or equalities, which would represent the constraints. And here, actually, it was the form of the model, optimization model. So, no, and here are a lot of algebra, of course, a couple of words, and a lot of Greek symbols. However, the solver algorithm that is going to solve that problem needs the models to look like basically a matrix or a couple of vectors. That matrix and vectors are a lot less intuitive than the algebraic notation that's on the left. And so in ample's role is to do the translate of what we have here into what the solver understands. Ample let us write something that looks like the model that we write down on a piece of paper and translates them into matrices and vectors that the solver needs, and then translate the results of the solver back into the something what we can read from here actually is the solution. Its code looks sort of like a blend of algebraic notations and computer code. There is a lot of stuff that looks like computer code. It includes keywords, comments, semicolons, and a lot of other syntactical things which we will review later on. So how we can install and run Ample? Very easy, by the way. In the Google search, we type in Ample free download. It will navigate it to the site from where you can download it. You provide some information required from you, and then you will receive a zip folder which you may store on your computer. No, first it is recommended to create a folder which you will use to store all your Ample related files. Then unzip the distribution file by double clicking on it, again, which you get from the site. Move all the files from the resulting folder into your Ample folder, and to run it immediately, just double click Ample executable. Ample supports three types of files. They are model, data, and run file. So the model file contains the mathematical formulation of the problem in general form with stats and parameters used to represent the input. The data file contains the description of the sets and values of the parameters describing the instance of the problem being solved. And the run file lists the instructions for AMPL to load the model and data files, interacts optimization solvers, and output the solution and related information. Remember that the files can be created and modified using any text editor. Me, for example, and it is recommended to use Notepad as the easiest text editor ever. Some interesting hints about AMPL basics. First of all, remember that Ample is case sensitive. So lowercase and uppercase letters represent different symbols. Variables. AMPL ignores white space. Your model will go into a text file, which we can later save as with the mode extension or DAT extension. You will type commands like solve at the Ample prompt line. Comments are denoted by a number sign, and every line must end with a semicolon. And please remember that even if it is a comment, I still recommend you to finish it with a semicolon so that you really develop this habit of ending every line with a semicolon. Now, the next three slides will represent AMPL basics of AMPL syntax for model files. Now, here actually what I want to point your attention, and this is what we will use today. That is the var keyword, which represents to introduce variables used in the code. And here actually it even introduces the type of the decision variable, and so even integer actually stands. Then the keyword which for the objective function. Please note that the objective function needs to be assigned. So a name needs to be assigned to the objective function. In this case, for example, a z followed by a colon. And after that, actually, you spell out the function, either minimize or maximize. Then the constraints are introduced using the words either subject to or its abbreviation as dot t dot. Then every constraint has a name. In this case, it is C1, followed by a column. No? And after that, you use an algebraic inequality or equation which describes the stated constraint. Then for the data file, you use such keywords as stat or parameter, which assigns values to parameters. And for the run file, okay, it's every problem. It is recommended to start every program with the word reset, which reset the ample environment and actually eliminates all the clashes and starts like the program from scratch. Then model, if you load a model from the example, and data, if you again load a data file. Then the keyword option specifies the solver type used in this program. For example, in this example, you have express, but also we may use here T-flex, lobby, minus, or any other solver supported by their AMPL executable. The line solve actually solves the optimization model, and the keyword quit just quit through the ample environment and closes the executable file. A display keyword actually is very useful as it displays the values of variable x and the objective function. And the close keyword actually closes the file used for output. Also, a basic of ample syntax involve such keywords which have been mentioned already, and some others, arc, some parameter. Reserved keywords for the program itself would be for logical operations, some other logical operations, and a couple of few. Arithmetic operations are standard. Plus stands for addition, minus stands for subtraction, asterisk stands for multiplication, slash stands for division, and with this arrow axis stands for taking exponents. Then functions, absolute values, sine, cosine, log, square root function, it's a function, and exponential actual function can be used too. And the commands display, write, print option include quit, so on and so forth, that it has been mentioned before. Comments are interested by the number sign, or actually you can use such symbols as slash asterisk for beginning and asterisk slash for the ending. And still, it is recommended to put a semicolon at the end of every line. For letters, you can use both lowercase and uppercase, but remember that this language is case sensitive. The best way to learn a software package is to start by running a working code and play with it by making changes. Of course, you are not expected to memorize all the ample syntax, but you should spend sufficient time with the AMPL to be comfortable running and modifying the examples provided in the textbook and at the lecture, as well as implementing similar models so you can use this knowledge to your advantage outside the classroom. It is important that you manage to install and run AMPL while viewing this lecture or after it, maybe simultaneously it will be different, but later on definitely it would be good. And the videos, also watch the videos suggested by the course developers, which are available either in the textbook or I will upload some of them. Make sure that you save all the AMPL files you're working with in the same folder where you have ample executable. Otherwise, you would need to specify the paths to your working folder in your implementation. Now, let's consider some of the examples. The first one, run a new maximization problem, example 1. Suppose a manufacturing company makes 3 products using 3 resources. The table below here, product 1, product 2, product 3, resource 1, resource 2, resource 3. Here we are. The table below provides the information on the number of units of each resource used to make 1 unit of each product. Now, here we may say that, so for product 1, you need 1 unit of resource 1. For product 2, you need 2 units of resource 1. And for product 3, you need 2 units of resource 1. Okay, so this is actually how we interpret this table. So the table provides, the units of each resource used to make 1 unit of each product, the selling price, here we are, of 1 unit of each product, and the available supply of each resource, here we are, expressed in the number of units. The objective of the company is to maximize the revenue by producing an optimal number of units of each product while not exceeding the resource limitation. So, referring to the algorithm which we introduced last time, the complete linear programming formulation will look like this. I will not detailing how we did it because we spent a lecture on doing it last time. So therefore, this is just the result of those steps which were supposed to be performed. So for the objective function, we have 4 times x sub 1 plus 3 times x sub 2 plus 5 times x sub 3. Recall that 4, 3, and 5 stand for the price. X sub 1, x sub 2, x sub, I forgot to say that as we have 3 products, it makes sense for us to assign the number of units of every product as x sub 1, x sub 2, x sub 3, which are our decision variables. So therefore, the revenue is calculated as the price times the unit produced, as referring to our problem, to our information. Actually, we will have such an objective function which represents the revenue, which needs to be maximized, according to that. So the constraints which we introduce with the word subject to, or s dot theta, the constraints are represented by 3 inequalities, and normally they introduce resource 1, resource 2, resource 3 limitations, and is composed of 3 inequalities. Yeah, x sub 1 plus 2 times x sub 2 plus 2 times x sub 3 is no greater than 4, because it is resource 1 supply limitation. Then 3 times x sub 1 plus 4 times x sub 3 is no more than 6, resource 2 constraint. And 2 times x sub 1 plus 4 times x sub 2 plus 3 times x sub 3 is no more than 8, which is resource 3 constraint. So remember that we always include specifications for the decision variables. In our case, we introduce non-negativity constraints for each of the given decision variables. Now, let's look at the AMPL code for this example more carefully. First of all, of course, I prepared it ahead using a notepad editor. Now, here we see the number sign. That means a comment, and this is where I just put for myself and for you that I prepare this code using Notepad, and it refers to example 1. Then I use the command reset. Reset is a highly recommended command at the beginning, which resets the ample environment in order to avoid clashes with the previously executed definitions of variables, constraints, and parameters. Then you see another command, again, is simple, command symbol, where I just specify that example 1 is prepared by me, Elena Valavik, and remember, okay, that I put semicolons at the end of every line. Then another command from that I will introduce decision variables, and here actually the declaration of the decision variables. Every variable declaration starts with the word keyword var. Then I demonstrate that this variable is a non-negative value for first variable. So x2 refers to the second variable, and x3 refers to the third variable. Recall that there are 3 products produced by this enterprise. Then next line refers to the comment, which just denotes that then we will work on the objective function. The objective function is needs to be maximized, so therefore I use the command maximizer. The name of the objective function is revenue, so I named it, followed by a colon which specifies the algebraic expression which is used for this objective function. And again, it goes exactly what we had on the paper written. It is 4 times x sub 1 plus 3 times x2 plus 5 times x3. Again, and I finish this line with a semicolon. Now here just additionally put my comment that I want to maximize the revenue. Next specification is again, it's a comment, my comment that then I'm moving to the constraint part. And every constraint is represented by introduced by the word subject to. Then I assign a name to every constraint. Remember that we had 3 constraints, and they were all resources related. So therefore, constraint 1, constraint 2, constraint 3, C1, C2, C3. Again, followed by a column, and then introduces the algebraic inequality, which demonstrates actually this constraint. Then next line, look here, keyword option solver. In this line, I choose a solver which I want to use. In this case, I wanted to use minus solver. Again, again, I put semicolons. Please note the semicolons everywhere. And put the word solve, which really prompts the solver to generate a solution. And then I ask to display all the required values of the number of units of every product and the maximum value of the revenue. And here we are. So here's what the ample executable represents, and he produces, actually not represents, produces. So and here we have the first part is just the code which you have just seen. Here it is, and then it shows you that the solver 5.51 was launched. It announces that optimal solution found, that there were 2 iterations performed, and the value of the objective function is 11. Then my command was display the values, revenue, x1, x2, x3, and here actually is the execution of this command. The revenue is 11, number of units for product 1 is 2, number of units for product 2 is 1, and number of units for product 3 is 0. So with this conclusion, so remember that optimization models are all about facilitating a decision-making process. So therefore, with the obtained result, we can come up with the conclusion that with the stated constraints, the company may reach the maximum revenue of $11 by producing the optimal number of product 1, 2 units, or product 2, 1 unit, and product 3, 0 unit. Now, the same problem, or just for variety, I used another solver, Groby, with the same code. Everything is the same instead of the option solver, Groby. And here we see that Groby version 10 is 0.4 and 0.1. Optimal solution, the objective value of the objective function is 11. So it always specifies that it uses the simplest method, and there were 2 iterations. Then my prompt to display the revenue resulted in this exactly in the same values which we obtained using the minus solver on the previous slide. Then last time we considered an optimization, we formulated an optimization model for Heavenly Pouch Incorporated problem. Well, I'm just reminding you that it was about Heavenly Pouch Incorporated, which produces 2 types of baby carriers, non-reversible and reversible. Each non-reversible carrier sells for $23, requires 2 meters of a solid color fabric, and costs $8 to manufacture. Each reversible carrier sells for $35, requires 2 meters of a printed fabric as well as 2 meters of a solid color fabric, and costs $10 to manufacture. The company has 900 meters of solid color fabrics and 600 meters of printed fabrics available for its new carrier collection. It can spend up to $4,000 on manufacturing the carriers. The demand is such that all reversible carriers made are projected to sell, whereas at most 350 non-reversible carriers can be sold. Heavenly Pouch is interested in formulating a mathematical model that could be used to maximize its profits resulting from manufacturing and selling the new carrier collection. And this is what we did last time, and we came up with the following model. We were talking about profit, so therefore this is the product price. We were talking about maximizing the profit. The company produced 2 types of products, so therefore the units, decision variables, we had 2 decision variables, non-negative. X sub 1, X sub 2, which denoted 2 products, 2 types of products produced, and 15 and 25 stand for their selling price. So, and here are 1, 2, 3, 4 constraints, and 1 more constraint, which again we recommended by our hints for non-negativity of the decision variables. So the AMPL, the AMPL program, again, I use Notepad for that, looks like this. So reset, again, remember that we just cleans up the ample environment so that all previous variables avoid clashes with the previously executed definitions of variables, constraints and parameters. So we actually cleaned the ample environment. Then I put 2 comments. Again, that it was prepared by me. Oh my God, I spelled out my name wrongly. Okay, and that actually this example refers to the Heavenly Pouch problem. And then I again commented on the part where I declare decision variables. Again, here I included the non-negativity constraint. And here again, just my comments that x1 refers to product 1, x2 refers to product 2. Again, remember about the semicolons, which are used at the end of every line. And here, actually, of this line, because it represents the program, the program itself. Then another comment, objective function, maximize profits. And there, I put down the comment maximize. Profit refers to the name of the objective function, followed by a colon, and then followed by the algebraic expression, finished with a semicolon. Then, instead of using spelled out word subject to, I just used the acceptable pretty short name for it. It is s.t. And again, every constraint is named to, followed by a column, and then followed by the inequality, or no, in our case, we don't have equalities, but either inequality or equality depicting actually every constraint. And every line is finished with a comment for us to be able to understand what's going on in the problem, even way later on after we need to refer to it. And here again, using the option keyword, I use the minus solver, and then just prompted the ample executable to actually to solve the problem, so, which produced the following result. The results in the following. Here is just the program which I entered. And here we have that version 5.51 was used for the minus. The optimal solution is found. It has 2 iterations, I think. And the objective function reached the value of $9,375. Then I prompted to display profit, product 1 number of units, no, decision variable 1 actual value, and decision variable 2 value. And here we have the summary. Profit is 9,375, as it was stated before. Variable 1 has the value of 125, and variable 2 has the value of decision variable 2 has the value of 300. So based on the obtained results, here are the results actually, we can make the following conclusion. Remember that we solve these models in order to facilitate a decision-making process. So the conclusion. With the stated constraints, the company Heavenly Pouch may increase its profit up to the maximum of 9,375, provided they will produce 125 units of product 1 and 300 units of product 2. And recall that one of the problems which we solved, in terms of formulating a model we solved last time was about a box. Yeah, I will just remind you that we needed to create a box with an open top and square base with a surface area of 300 square centimeters. And we needed to find the height, which will produce a box with the maximum possible volume, the height and the side measurement actually. So there were 2 variables. Okay, and here's actually the model. Yeah? So interesting gleam is that the objective function is non-linear, as you see, actually cubic, and the constraint is quadratic. It is non-linear either. And of course we have non-negativity for the side measurement and for the height measurement for the both decision variables. For this problem, we will use the NEOS server. First, in Notepad, like we did before, we spelled out the instructions to solve this problem. What is interesting here? The same. Comment, 2 decision variables, and here. As it is a non-linear problem, we, using the command let, we assign the initial value for the given variable. Technically, even though we put non-negative, technically it needs to be greater than 0, right? Because distance cannot be 0. So therefore, we start with the initial values for side measurement, for the height measurement. Then the objective function, we introduce the objective function, and we give it the name of volume. Then we assign it the expression x1 squared times x2, and you see that the name is finished, is followed by a column. Yeah. Then the constraints are introduced by the constraint C1, which has the name of C1, followed by a column, and the equality x1 squared plus 4x1 x2 equal to 300. So then we prompt to solve this problem. Look here, as we are going to use NEOS, the NEOS server, I do not specify the solver in the comment here. And later I will show you why. And then I prompt to display the values of volume, x1 variable and x2 variable. After its execution through the NEOS, we obtain the results. Now here, by the way, what I said, that every job is assigned number. Here's the password. Here I shall give some more information that informs on two variables, one constraint, one nonlinear objective. Yeah? And here I used the minus 5.451 solver. It went through 75 iterations, by the way, and the value of the objective function was 500. This is the volume. The side measurement was 10, and the height measurement was 5. So therefore, the conclusion, which can be made based on this computation, is that the maximum volume of a box with a square base, provided that the surface area is 300 square centimeters, is 500 cube centimeters, with the side measurement of 10 centimeters and the height measurement of 5 centimeters. Now, with this being said, actually, let's come to practical implementation. I'm finished with the presentation, and I will move to, I will close it, and I will move, I will close it completely. And I will move to the side. Yeah. Okay. I'm launching the NEOS server. Okay, here we are. Okay. Here it is. Here. So now you can see it. I hope that you can see it. No, and look, please, at the first page, which you will go using the link which was specified on one of the sliders, or one of the first sliders here. No, and you see that this is the layout of the NEOS server optimization. Then it consists of several grouping information, NEOS server, NEOS guide, advanced tools. So let's go to the simplest, submit a job to NEOS. Here we are. Okay. Now, here you see problem types which can be solved using NEOS server platform. And here they are. Bound constraint optimization, combinatorial optimization and integer programming, complementary problems, extended mathematical programming, global optimization, linear network programming, linear programming, mathematical programs with equilibrium constraints, mixed integer linear programming, and so on and so forth. Here we are. All types of them. Stochastic linear programming, this is what we mentioned. Now, look, no, I will look whatever, minus, for example, here, see? Here we see that in the brackets which follow each type of solver, you can see the algebraic modeling programming languages which are supported by this specific solver. And what these brackets follow whatever solver in this list, what each of them. For example, Gurobi would here the four algebraic mathematical programming languages which are supported by Gurobi, for example. No, and so on and so forth. So this is no, and you see that AMPL really significantly almost dominates, and GAMS is used by a lot of them. So therefore, definitely AMPL and GMS are one of the among the most used languages for solvers. Then, no, for example, I want to solve the problem with the box and it is nonlinear or nonlinear. No, let's use minus. Here it is. We use now minus. Let's do with minus. Okay, ample. Here we are going, okay, to the web submission form. So in fact, you saw it on one of the slides. Okay, observe. So we need to browse through the problem, and here it is in my folder. Example 2, volume. Now we're talking about volume. So NEOS. So this is, I specifically prepared this code for the NEOS server. Here we are. We are opening it. No. Okay. Let's put down the comments like lecture 3, box, volume, problem. You may put whatever you want. Okay. Comments. Then, okay, I want the solution being delivered to my email. It is already here. And submit. Okay, no, almost immediately it produced the results. Now here what I said, the job number is assigned to it, the password, then actually it indicates which solver which used and which language was used. Here is minus AMPL. The starting time was 11:25:36 and the end was 11:25:38. Actually, it took 2 seconds to solve this problem. No, the problem was not really difficult. And here we see the results. No, first of all, the report that there were 2 variables. That is true. There were 2 variables, all nonlinear. That's true. 1 constraint, again nonlinear. 1 equality constraint. That's true. And optimal solution found 75. Oh my gosh, it took 75 iterations, and the value of the objective function was 500. Then I asked to display the values of volume x1, x2, and here we are 500, 10, and 5. And remember, actually, I entered my email address, so therefore, just to testify that it really works, let's go to my email box. Here we are. And here is the report, which I obtained at 1925, so actually the last one. And actually exactly the same what we have just seen on the screen actually was navigated to my email address just because I asked it to do so. Now, as you see, there are a lot of reports here just because I solved a lot of problems. Okay, I will close it just because so I just testified that it is really true. And let's solve another problem. Linear programming. Linear programming. Oh, linear programming. Oh, Gurobi. Okay, let's use Gurobi solver for Heavenly Path. Here we are. Again, the problem was prepared before. Here I have this code. Here we are. Okay, let's put a comment again. Lecture 3. And pouch problem. Okay. Again, I prompt it to send the result to my email. No, and I submit. What do we get? It is awaiting results. It says awaiting results. No, and here we are. We obtained the results, which you could see on the screen. It is 9,375. Variable 1, well, the number of units of product 1 is 125, and the number of units for product 2 is recommended is 300. And so therefore, actually, you see that NEOS works. It is free of charge, and I highly recommend it to use it. And one more thing which I wanted to just I will close this one, and I will open another my folder. And here. Come. Here we are. Okay. I look at my folder. I downloaded AMPL here. I created a folder as it was recommended. Generally what you download is just a zip package, so which I unzipped into AMPL MS Win64. I've zipped everything here. Now let's open it. And here you see this is AMPL executable. And here within this folder, you see a lot of suggested solvers, what amount they're there, what which we mentioned, what minus should be here. Here's minus, here's Cplex, what group is here, Cplex, and actually a lot of others. In fact, in the docs file, or in the docs folder, I'm sorry, you can see the description of each of the solvers and what type of problems it may solve. Okay, then let's consider the examples which I introduced before. Example 1, yeah? Okay, here it is. And how to do it immediately from the AMPL executable. Okay, and wait, where's here we are. So example AMPL. So and here actually I paste in the code. Here we are, the solver. We have it, and then I prompt to display the results. What will there, by the way? X1, X2, X3, and the objective function was revenue. Semicolon. Here we are. Well, I'm storing. You see, I mistyped it. Good. It's good that I made errors. X2, X3, revenue, and then, yeah, let's check it out. Revenue, yeah, that's semicolons. Okay, let's try again. And here we are, we have the revenue of 11, 2, 1, and 0. This is exactly what we saw on the screen. Let's okay, we did that is okay, wait. So I want to terminate the session. I close it. And one more problem which was on the slides. That was heavenly pouch. Heavenly pouch example. Repeat. Ooh. Okay. Okay, again, I implicitly stated the solver which needs to be used. Then I click the button, optimal solution found, and I prompt to display the values. And the values were, what is the profit? Profit, X1, X2, 2 semicolon. I spelled everything correct. Okay, here we are. And here the values which you could see on the screen before and in the slides. 9,375 is the maximum of profit. The product 1 volume is 125 units, and product 2 volume is 300 units. I terminate the session. And here we are. Okay, that's it. That's it. So with this, thank you very much for attending this lecture. I hope that you have learned something new. Then I will post assignment. The title is going to be assignment 2 for you. It is not going to be easy, just try to use it a little bit. So therefore, in this assignment, you will need to spell out the code for any of the given, those which I have already solved and which codes have been already prepared for you. So the only thing which you will need to change is, instead of prepared by Elena Volovik, just you need to put your name, prepared by, and your name, and really enjoy how program works, how you receive the results. And you will need to do 2 versions, one to solve the same problem on the NEOS server, and another one is to use the AMPL executable file to actually find the solution too. Thank you very much. I will see you next Thursday, and happy holidays to you.